Okay, so this is chapter 17, Crystalline State, that I will be focusing on. So from the previous section that I was talking about amorphous polymer, this is about the semicrystalline polymer, and so this is regarding the chapter 16 versus chapter 17. And this is a little bit more expanded section than I usually cover in my previous classes in my polymer chemistry class. And this chapter 17 is a textbook of our textbook, the Young and Lovell, and they are actually quite active in the area of semicrystalline polymers and also the mechanical properties of those and crystal structure studies and so on. So this one is actually go into quite an in-depth on the semicrystalline polymers. Semicrystalline polymers are crystalline state is coming from the semicrystalline polymer, and then I will divide into many sections. And this one is focusing on essentially general overview. And you heard about the glass transition temperatures, right, in the chapter 17, and this is the TG of the polymers that have actually, even for the semicrystalline polymers, you have a TG of a minus 23 and TG of 100 for polystyrene, and this is for polypropylene, and this is a polystyrene, and so on. And if you go to the neighboring side, and this is essentially for the one that's what they call the side group, this is essentially same as the vinyl polymers. And if you look at the polypropylene, the melting temperature, it says about 190 degrees C, right? And then if you go to the polystyrene, it is about 240 degrees C. Okay, so the melting temperature is certainly higher than the TG, and that has been always the case. And there is because the polymer has to be softened. Okay, so if you have a TG, right? So this is one of the diagrams that you should keep that in mind. If it is a semicrystalline polymer, they have a TG and the TM. As you heat, right? This is a glassy, and this becomes a rubbery. And then I'm talking about something in the what it calls the amorphous phase of the semicrystalline polymer. In the crystalline phase, and there's this is still crystal. So still they maintain the crystal structures, and eventually the crystal structures are being lost when you heat it above the melting temperature, and then you will see essentially the rubbery state. And in the state of the rubbery and the temperature higher than TM, both phases are rubbery, and the processing is possible. Okay. So the melting temperature is a lot more important criteria for them to define the processabilities for semicrystalline polymers. So some polystyrene is actually this is I think they're coming from the syntactic polystyrene. Atactic polystyrene do not have a melting temperature. So it's a melting temperature is combined with the tacticity of the side group as well as the chemical structure combining those. Okay. I just wanted to give you a general concept, and this is essentially TG versus the TM in terms of the Kelvin, and there is actually going to the almost like toward the end of the chapters. This gives an idea about usually the TM is smaller than TG is smaller than TM. The ratio between TG over TM is about between 0.5 to 0.8. Okay, and it's that's something that good guidance for you to know, and people are interested into looking at different kinds of polymers, and it's a good practice for you to know how to write the chemical structure of those polymers. I think that you should know it by now. Polyethylene oxide is essentially CH2 oxygen, and from the ethylene oxide ring opening polymerization, and that's what we call the PEO. And the bio people also call it a PEG, right? Polyethylene glycol. When I start in the chapter 16, I show the wide-angle X-ray scattering structures on the amorphous polymer. So this is an amorphous halo of the polymers, which is a pretty broad peak, right? And now I'm just showing one of the example of chapter 17. This is coming from the polypropylene, CH2, CH3. Okay. And this is made by Ziegler-Natta polymerization. Actually, Natta is the one who was very big on the polypropylene. It's a very nice property. Polypropylene is being used for your soda bottle caps and a lot of the clear, transparent plastics. Actually, they control the crystal size, so they may try to maintain the clarity, but the mechanical property is just right, pretty good for the polymers. And as you can see that there is a sharp band, and this is a sharp band here. There's many bands, and this is A, is what we call the isotropic melt, because you have a lot of crystals are having a various orientation, and the B is an oriented polypropylene fiber, so PP can be oriented, the crystal can be oriented with the drawing direction, and you start to see more like what they call the diffraction peak, diffraction patterns, using the two-dimensional detectors. And so it's a sharp peak. So when you writing the 2 theta over the intensity for the wide angle, you will see the multiple peaks, and from the small and wide angle X-ray scattering. So it is related to the crystal structures that I'm going to go to the details on this. Okay. So next one is I'm going to talk about the solution group grown, the polyethylene single crystal. Single crystal structure is very important, and provide a very good insight for us to understand finally the structure of the melt polymer, semicrystalline polymer in a state of the bulk. Okay, so let me move on to the next one.